A mechanical loom weaves complex patterns through repetitive, automated precision. Software operates on an identical principle, moving from manual execution to systemic automation. In a standard code editor, repeating a task without a dedicated control structure requires every action to be written out manually, line by line. While typing 10 lines is manageable, parsing a database of 10 million records through manual sequencing is physically impossible. This brace collapses that redundant stack into 2 lines of code. This is iteration, the mechanism that allows code to handle increasing task volumes without increasing its own length. A single block of instructions can now repeat itself, processing data volumes that would otherwise require thousands of lines of manual input. Python manages this process through 2 distinct control flow architectures: sequence-bound iteration and state-bound iteration. Understanding these 2 architectures allows a developer to replace manual repetition with automated logic. The sequence-bound architecture is defined by Python's for loop. This structure is built to move through known, finite sequences. When the data volume, like a list or a string, is defined before execution, the loop iterates through those specific steps. The range function generates these sequences using 3 arguments: a starting position, a stopping boundary, and a step interval. The loop extracts each value from the sequence one by one, temporarily assigning that value to the variable I for processing. If you provide only a single argument, Python defaults to 0 as the starting point and stops just before the designated number. This same extraction logic applies to text. The loop isolates and processes each character in a string sequentially. It functions identically for lists, where the loop moves through each discrete element from the first to the last. Sequence iteration is the primary tool when the exact volume of data is known before the code begins its execution. When the length of a task cannot be predicted, Python utilizes a state-bound architecture, the while loop. Instead of following a fixed sequence, the while loop executes as long as a specific Boolean condition remains true. In this sum of numbers script, the left side of the screen monitors the Boolean condition, while the right side tracks the variables in memory. During each cycle, the script adds the value of I to the sum variable, updating the total. An explicit increment step is required to drive the execution forward, pushing the value of I toward the boundary condition. Omitting this step prevents the variable from reaching that boundary, resulting in an infinite loop. Because the condition never resolves to false, the code repeats perpetually and can lock up system resources. State-bound iteration allows a program to react to unpredictable durations and changing internal states. Standard loop cycles are predictable, but execution modifiers allow for more specific control over that flow. The break statement acts as an exit. When the program hits a specific condition, it ejects from the loop immediately and moves to the next block of code. This allows an algorithm to stop a search the moment it finds a target value, rather than finishing a sequence of millions of empty rows. The continue statement skips the remainder of the current cycle and snaps the program back to the top to start the next iteration. This creates a filter, allowing the loop to safely bypass specific data points while the broader process continues. The pass statement performs no action. It is a placeholder used to satisfy Python's indentation requirements during development. These modifiers provide control over loop execution, enabling specific logical exceptions within a general automated process. Programming reaches higher dimensionality through nested loops, where one loop is placed inside the block of another. In this hierarchy, the outer loop pauses its execution until the inner loop completes its full cycle. This 2D grid shows the spatial relationship. The outer variable drives progression down rows, while the inner variable populates data across columns. The inner loop's boundary can be bound to the outer loop state, causing columns to stop populating based on the row number. By iterating this way, the program constructs complex patterns row by row, with each inner loop cycle building upon the position of the outer loop. Nested loops bridge the gap between simple linear sequences and multidimensional data structures. These mechanics are the building blocks for standard mathematical logic problems. Prime number identification uses a loop to test sequential divisors against a target, checking if the remainder is 0. Efficiency is gained by adjusting the range function to skip unnecessary checks, reducing the number of iterations required. Generating a Fibonacci sequence similarly uses a loop to calculate each new value from the sum of the previous two. The loop manages the constant swapping of two variables in memory, advancing the sequence with each cycle. Detecting a palindrome, a value that is identical forwards and backwards, requires reversing the data. A while loop extracts an integer's digits one at a time and reconstructs them in reverse order. The logic concludes by comparing this reversed output against the original number stored in memory. These complex mathematical results ultimately emerge from the precise orchestration of sequential iterative steps and constant memory updates. Programmers choose between these structures based on the data, the for loop for known sequences and the while loop for conditional states. High-speed server racks process millions of concurrent loop executions, utilizing these same basic control flow structures to manage global infrastructure. While loops govern systems like ATMs, which wait in a loop for a specific user state change before granting access. Data processing pipelines use nested for loops to parse and organize the rows and columns of massive databases. Iterative cycles also drive the training of AI models, where algorithms process vast datasets through repeated epochs. Mastering these control flows translates logic into scalable computational action.